Okay, now I can share my screen here. Hello, good afternoon, everyone. Today I'm going to discuss about the topological insulator and quantum computing. I just first of I just in here I will discuss on the history of the topological insulator and quantum computing, and I will give a little bit introductions of topological insulator and quantum computing, and what are the challenges on this topological insulator and quantum computing, and also and how we can deal with this challenging on topological insulator and quantum computing, and what is the correlations between the topological insulator and quantum computing. And these things we are discuss on here. So first of all, I'll share my first slide here. This is just heading here, and this is nature space topology. This is quantum computer, looks like that. Okay, here is the definitions. What are the quantum computers here? Okay, let me go to the next slide. Okay, the history of topological insulator and quantum computing. Okay, the history is the topological insulator concepts open after the discovery of the quantum spin-off effect in 1980. Okay, but the model of the three topological insulator is proposed in 1985 by the two physicists Polkov and Prakun. And there are two types of topological insulator. Okay, the one is two-dimensional topological insulator and three-dimensional topological insulator. Okay, and the two-dimensional topological insulator is proposed in 2005 by two physicists Ken and Mill. Okay, and the concept of the quantum computing and this is for topological insulator, and the concept of the concept of the quantum computing were given by the Richard Feynman and the Yuri Menin. Okay, these are the two. Richard Feynman is a physicist and Yuri Menin is a mathematician. And before that also, before that time also, the concept was come. But Richard Feynman, after the Richard Feynman gives the lectures. It was organized by the IBM and the MIT University, and at the time he gives the lectures on quantum computing, and from that it was boom up. Okay, and his lectures was published in 1984 um, by the by the International Journal of Theoretical Physics, and his lecture was published from there, and from that time it was a boom up. The first quantum computing was built in 1985 by Isaac Stone. This was built in Los Angeles Laboratory. That's the MIT, California University, California, Berkeley, like that. Okay, and they built first two-qubit quantum computer. Okay, in the first time, they built a two-qubit quantum computer, and which was loaded with the data, and the solution is the output. Okay, which was loaded with the data. Okay, which was loaded with the data and with data and gives solution is the output. Okay, and the solution is the output there. Uh, okay. And this is the three topological insulator in three-dimensional and two-dimensional. Okay. This is a topological insulator in three-dimensional and two-dimensional. Okay. And this is topological insulator in three-dimensional and two-dimensional. This is 43. Other figures also there, but I just it's like this one. Okay. And this three-dimensional topological insulator, and this is for two-dimensional topological insulator. And this is the quantum computer which was built in Google here. Okay, and the temperature of this this one have a higher temperature, this one have a little low temperature, this one has a low temperature, and the chips was used in here. Okay, microprocessor, and the main thing was here. Then all of the research also was going on here to develop the how can we build up the microprocessors. Okay, so whole attention was all over the old people are working on that things. So how can we build up the the microprocessors which can be maintained the superposition states, and so we always have the enhanced time. How can we enhance the coherence times like that? Okay, and this is for coolant we have to use, and we wrap up this one for the cooling one, for the for cooling. Okay, and then for cooling is needed there because to maintain the superposition states. Okay. And okay, and this is the quantum computer which was built in IBM. IBM. It is not called it is not completed. Okay, it was just it was in construction. It was built over here. Okay, and it's also and yeah, it's all the always part is made of the gold. Okay, and in here in between below this one region we put the microprocessor, and whole thing is here. We have to do research in here and to make how we can build up this topological insulator I just mentioned in previous time in previous slides also. So there we are trying to build up the we have to build up the now we are trying to find out the hardware. Okay, and so we are trying to identify the different materials, try to find out the different materials, so we can so that's why it will maintain that's why it will be that's why it will maintain the superposition states. Also keywords will have to be preserved for up to long time, and there will be the high coherence time. So we have to use try to explore the different materials. What we use here silicons here. Okay, this is the quantum computer of the Poly University. Okay, this is one of my friend, and he's also doing experiment on that. It's also quantum computer here, and it is also here. We have food here microprocessor, and he's also from our department. Okay, and CTV is graduate from there, and this now he's doing research over there. And he's a PhD in research scholars, and then he was the PhD researcher on there, and he's doing research also on this quantum computing. All right. Now let me I'll just tell me a little bit about the history of quantum computing. What are the history of the quantum computing? How it was originated? Topological insulators. What the topological insulator concept was come up here, and what is the history of the topological insulator? What is the history of the topological insulator and quantum computing? I just mentioned there. Okay? I just mentioned there, but I will tell you a little bit about the introductions. Okay. Um, mm. It is a topological insulator are the materials which interior is just electrical insulator and its surface is electrical conductor, which means electrons can move only on the surface. Okay. And generally, we know that the in conductors are the um, can conduct the electricity completely. We don't consider like that its surface can conduct interior but not conduct. In insulator, we consider whole insulator is non-conducting. Okay, but there are some materials we found that whose surface can be conduct the electricity, and interior surface it is an insulator. Okay, which means that surface can move the electron surface of the topological insulator. The electrons can move, but in interior the electrons cannot be moved. So the well-known topological insulator is now is gallium arsenide. Okay, it is the two-dimensional semiconductor, and which is used in the integer quantum Hall effect. Okay, experiment. Okay, integer quantum Hall experiment. Now, the new generation topology is the bismuth selenide. Okay, it is not that much widespread, well known on that one, the things. This one, but this is also a new generation topological insulator, so bismuth selenide. Okay, and we are classify the quantum computing based on the quantum mechanical phenomena. Okay, quantum computing is computation based on the quantum mechanical phenomena like superpositions, entanglement, interference, decoherence, coherence, like that. Okay, so it is based on that quantum computation is based on that things phenomena. Okay, these things were happening on the microprocessors. Okay, with these phenomena are the exhibited by the quantum. These are the quantum behavior. Okay, so we are using this behavior here to so they are the these superpositions, entanglement, interference, decoherence, like that. Also, it will be the used for the computation process on quantum computing. And this is just a slide figure, okay? I just want to here, okay? And it is a refrigerator here. This is refrigerator. This is data, binary readout. Okay, data was entered here, and this terminal is user, and this pop-up here. This come again, come back to the data center, okay? This is just a figure I just given here, and our temperature was different. It's selling here, okay. All right. This is the microprocessor which was used in IBM, is used in the IBM, okay, and it is unpacking IBM 127 qubit quantum. Look at here. Is we started from the qubit quantum processor. Now we are reached up to the 127 qubit processors, okay, and this is the I was taken the this is the microprocessor. I was taken the domain here, and this is the regions where the qubit is placed. Okay, this is the here, and this is the resonator, micro resonator. It was passed from here. It is maintained for the superposition states. Okay, it seems to look like that. Okay, and in a domain here, and just I just to show you here. Okay. All right, and the SCAMOR processor. It is the microprocessor which was built in Google, and this is the SCAMOR micro. Is Google's Google quantum computer. Okay, and it is the microprocessor which was used in this quantum computer. Okay, and this is the microprocessor. It is called a SCAMOR microprocessor, and it have the 53 qubits. Okay, and in 2019, so they announced that they built off they are able to do computation styles, which is requires to solve the same computation styles in IBM's highly powerful supercomputer summit supercomputer. It will take more than 100 million, 1 million years, okay, like that, okay. But some of still like that, it is 20,000. Some of this like there was no same voice, okay. But mm, the input, if you go and see on the website also, there was written that it was took up to 10,000 year like that, okay. But in overall, you can say that they have found the uh, may have cracked it, the quantum supremacy state, okay. And they have just done there here, okay. And this is just a block diagram. I've just shown you there how these, what are the procedure, what are the things it works. I think it is not that much clear. So I will written down, but I will explain here. And this is the software and the data input here, and it's come from here. And this is the classical computer. Okay, this is the electrical writing. Okay, and this is the quantum gates which are used in the quantum computer, okay. And this is the from quantum gate, it is go to the quantum register or physical as logical, okay. This is quantum shift, okay. And the whole thing was going on here, okay. All the entanglement, superpositions, and everything was going after the calculation computation task was completed, and the quantum interference and phenomena will be, this is the measurement interference phenomena, okay. Quantum field interference would become due to quantum interference, and if there was constructive interference, the whole superposition states will be collapsed, and these things will be happen. Okay, that's the measurement interference, and the electronic reading will be and the same as it is, and it goes to the data center. All right. Now I just show the what I'm just trying to describe the component of the quantum computer here. Okay, and this is the coolant here. I guess we have to use this refrigerations, okay. And this is the quantum computer. Previous time I just showed you. It is just just showing the particle figure here, okay. And this is the data center, okay. Well, now we have to. This is for input one, and this is for output one, okay. From data we have raw data. We have to insert input, give input, and raw input data here. And this is the analog electronic converters, okay. And this is the data, and this is the qubit signal amplifier, okay. This is qubit signal amplifier, and superconducting lines, it is used for the maintain the superposition states, and this is vacuum. And electromagnetic shielding is that we have to resist from the external environment, okay. So to maintain the superposition states, okay. So and then it is goes to the radiation shielding, okay. And qubit amplifier is, radiation shielding is there, okay. Electromagnetic shielding, radiation shielding, okay. We have to maintain there, and this is the quantum processor. Whole thing will be gone on there, okay. It is the main thing of this quantum computing, okay. And this thing data was gone there, and the computation process will be gone. There will be the superposition stage, there will be the covariance, okay, and there will be the entanglement. Everything will be happening on this qubits, and it mainly qubits are for qubits we use the electrons, atoms, ions, the photons, like that. Okay, it depends on what type of that, and depending on that, based on that we also categorize the quantum computers. Okay, so quantum processor, okay, and after computation stacks was finished here, and then it is a qubit amplifier was come on there, okay, and it is the same scenario, same things happening on there, and then we have to go on there, and the after computation stacks, finally will come here, and due to quantum interference, so it was converted superposition state to collapse, and it's converted into the beta, okay, and it is converted binary data, and we have to store in the data center. All right. And now we discuss on the difference between the classical computer and quantum computer, okay? Or what is the difference on classical computing and or quantum computing, okay? And this is generally the quantum computing calculates with the keywords which represents the both 0 and 1 at the same time. And classical computing is the which calculates with the transistor which can represent either 0 or 1, okay? The main thing of why we are using quantum computing in the place of classical computing is that classical is we can do the computations by classical computing also, but the computation time for the by using the classical computing is very high, okay, as compared to the quantum computing, okay, and the quantum computing it was using the quantum parallelism, so that's why we can be do very fast. Like I'll give the examples that suppose I want to go to is we can use that as an example, but to understanding I will give an example for that. Suppose if we wants to go to the to Palpa, okay, and from Kathmandu to Palpa, and there are so many ways, okay, so many ways to go to the Kathmandu to Palpa, okay, and if you use the quantum computing, it is used the superposition states, and it can change the number different ways at the same time. Suppose it means that there are so 5 ways to go to Kathmandu to Palpa, then it will choose the which one will be the shortest path, okay, and at the same time, and it will select the shortest path, and that will be that is the interference, due to interference, constructive interference, and other thing possibility will collapse, and the result will come there. But in classical computing, we cannot do like that, okay. If suppose there will be no superpositions. There are 5 ways, but it will check individually. Okay. First of all, it will check one path, and later, and then next time another path, and another. So it means one by one by one by one one by one. It will check that. That's why the classical computing will takes that more time in the computation. So that's why we use these superpositions state of the quantum particles qubits in a quantum computing. Now, power increases exponentially in proportion to the number of qubits. Okay, so if we increase the number of qubits, then the power will increase, the computational power of the quantum computing will increase exponentially. Okay, but in classical computing, it is a linear. Okay, power increases is a linear. It's one-by-one relations. The number of transistor increase the number of transistor, power will be increases. But it is it is same. Okay, and this is the relationship. Okay, and a quantum computer have the high error rates and the need to be ultra code. Okay, ultra code. Okay, so quantum computers have the high error rates. Okay, actually, that's the main challenge. Is how we can make the error less. Okay, how we can make the less error without using the high quantum computing. How without using the high qubits. Okay, and I'm right that we need the ultra core. It's not for all the types of quantum computers, but we need use the this ultra core. Okay, for certain like the superconducting superconducting circuits like that. Okay, we use the ultra cold like that, this one. But if you use the photonic one, we don't have to use the ultra cold. Okay, that is one of the solutions, but there are some problems, but we can replace by ultra cold condition on that thing on computers. Okay, and classical computers have less error rates and can operate the room temperature. That's the one of the most significant of the classical computing. Okay, all right. And the well-suited tasks for like the optimization problem, we can check the lot of possibility, okay, at the same time, okay. But in classical computing, we have to check the different possibility one by one. Okay, that's the difference on classical and computing and classical computing. Okay, and uh, and the data analysis and simulation. This is the one of the most significant use of the simulations. Like that, we want to understand how the universe was created, in the beginning of the universe, Big Bang, dark matter, dark energy, black holes. Okay, even how can we simulate the atoms, molecules, so many things. If you are able to simulate the if you are able to simulate a lot of these things, then we can understand how the particles will interact, how these, what is the sort of interactions, so what is the physical property. We can predict the futures also. Okay, that's why it is a lot of huge power, and that's why we have to focusing on this quantum computing, to do with a lot of computational tasks. Okay, and the most everyday processing is best handled by the classical computing. And we are not choosing that classical computation is not good for us. It is also good, but computation time was high, to solve a huge big problem, the big problem of the universe. So we have to develop the such type of computer. We can have the high computation power. Which can use the quantum behavior. Okay, or you can use the quantum behavior. Okay, we have to use this quantum mechanics. But in classical computer, we have literally we have to use the superposition state. Okay, and entanglement. Okay, the model of the computations for quantum computing, there are it is based on the basic element in which the computation is decomposed. Okay, in Git array, it is decomposed computation in the sequence of few qubits quantum unit. This is the quantum circuit diagram. Okay, we can this type of how we can arrange this quantum qubits. We can go in the IBM source, IBM lab there. Open, it is an open source. You can go on there. I have no time, much more time to say here. Okay, so that's why I just show the figure here. So mm this is the head and tail, head and tail, head and tail. Okay, it's a T dragger. Okay, you can check that, and we have to make the QE sorted. Okay, quantum sorted in the head. And so we have to use this one, and I'll just base for the pictorial figure here. All right, and this measurement based quantum computer, a measurement based quantum computer decompose computation into sequence of Bell state measurement and the single qubit gates. Okay, I just to mention there. Okay, I will have to use this one also. And elliptic quantum computing, it is based on the topological annealing, which decompose quantum computations of certain continuous transformation, initial Hamiltonian to final Hamiltonian. Okay. This one is also here. This one is main focus on that. Okay, the topological quantum computing. Okay? A topological quantum computer decompose computation into braiding for anyone's in the two dimensional lattice. Okay, and this is one of my favorite focus, topological quantum computing. And the significance of quantum computing. Okay, what are the significance of quantum computing is there? The quantum based cryptographic system in we are more secure than the traditional system. It is the encryptions. Okay, quantum computing have the high encryptions as compared to the classical computer. So we can that is a I don't know if there maybe in the futures they will find out some loops on there for hacking. But at present time I cannot say present time I can say that it is a very high encryptions, and there was no possibility of seeing hacking on the quantum computer. Okay. And the well-known quantum algorithms is a source algorithm which is used to solve the hidden solvable problem of abelian finite groups. Okay. It's the we have to build the algorithms like that so we can maintain the superposition states of quantum particles like that quantum qubits. Okay, and it has one is the source algorithm. Okay, and another is the simulation of the quantum system is an important application of quantum computing, like the simulation of atoms or particle in algebraic and usual condition. We get a lot of the atoms, molecules, and we have the particles. So we have to produce particles produce in a collider, and it has in unusual conditions. So that at the time we found that. Okay, so we have to solve these particles interactions to solve this particle interaction. How we have found this one, we have to use this one. Okay, all right, and this is just one of the example I want to show you here. Okay, this is the molecule of caffeine. Okay, it has just for by using the highly most super powerful computer in the world. That is the Summit Super Summit Summit supercomputer. Okay, it is a an IBM. Okay, and its power is just 200 petaflops. Okay, and if you give the that supercomputer also to simulate that one molecule of caffeine, it took the 1 into 10 to the power 16 times the age of the universe. That much time, it is greater than our age of universe. That much time we have to wait to simulate on this quantum on mm, uh, the classical computer. Okay, but if you syntax, if you go to the gives the for the quantum computer, just single caffeine molecules contain just only 180 38 electrons. Just so you go and see that, I just show you. Just look at just if you calculate the number of electrons, it's just 128, and the number of atoms is just on 24. Okay, so it means for that one, for that molecules, it took just only 164 qubits for simulations on that computer, on the computer. Okay, or just in the range of 120 to 200 kilometers. But for classical computer, it requires 10 to the power 48 qubits. Okay, and then the for our also have the 10 to the power 50 order of atoms. If you go like that, okay, to build consider all of these things. So approximate, no, it is not exactly, but there are some formulas also how to calculate here. But okay, now challenges on quantum computing is that scalable number of qubits and coherence time. The challenge on the quantum computing now in the present time is that we have to build the a high number of keywords, but we have to focus on the quality of the keywords also. Okay, we have to focus on quality of the how we can build the quality of keywords. Okay, and the another is just the coherence time. Okay, coherence time is that we have, it means that we have to enhance the length of the superposition states for a long time, the how we can enhance the coherence time. Okay, so we have to use this thing also. So what I have to find out the techniques, and then what are sorts of materials we have to use on that things, to I have to find out the for the to enhance the coherence time. Okay, we have to use here. Okay, that's it. Thank you.